Hey Abhishek, am I audible? Hello? Abhishek, can you hear me? Okay. So I'm audible, right? Can anyone confirm? Good evening. Akshay, Abhinav, Abhishek. Can anyone confirm that I'm audible? Okay, thank you, Abhishek. That's great. So, see, there was a mail celebrating that today's class is cancelled. Okay, probably that's the reason why very few students have joined today. But it was just a miscommunication. So, class is going to be held regularly. Okay, so I'll just share my screen. So, before today we start our lecture, you people have Aspen with you, right? I'm hoping that you have Aspen with you now. Can you please answer the question on the poll? Among five or only four? Only one note. Rest, you don't have Aspen with you now? Arey, please respond. Yeah, unless I get a response, how would I proceed further? If you don't see any poll, you can just put a message on the chat box saying you have or you don't have. That will work for me. Okay, fine. Anyways, I'll get started. Can you tell me your status to where could you finish? Previously, I gave you an exercise as a home assignment and asked you to finish it off. So, could you people finish it off? I remember Akshay was in last class. So, Akshay, could you do that? Even, yeah, Raj was also there. Okay, just trying. Hi, Raj, could you finish the assignment, the previous one which we were discussing? Raj and Akshay. And I remember both of your names. Anyone else who were also present in the last session? Akshay, any response? Partially did it. Okay. So, do you have Aspen now? Can we finish it in today's session? Okay, great. And Mr. Raj Mehta, what about you? Could you finish it off? No. Okay. So, do you have Aspen now? Shall we do it in this session? Or you don't have Aspen, is it? That's you are at job. Okay. And else, do you have access to Aspen now? Sriram, Abhinav, Abhishek. Okay, Abhinav, you have access. That's great. So, did you attend last class, Abhinav? No, you didn't attend. Okay, fine. Just wait a second. So, only two of you have Aspen with you. Okay, so maybe we'll finish off where we left last class. So, welcome all of you to the tutorial session of this series. So in this week, professor was basically giving you two case studies. One is based on synthesis of methanol from syngas, and another is based on synthesis of a reaction where two CSTRs were held in series and then try to find out the output conditions, right, for the given reaction condition. So post that, no, I have only couple of questions. Okay, so can you just answer quickly which among these are the module pellets available in Aspen among the four given? So among these four, there are a couple of model pellets which are mainly for reaction systems. Okay, can you just answer? Okay, let me show you the Aspen. So if you go to the Aspen pen, you can just see the reactor under model pellets. If you go to reactors, you'll be able to see 7 kind of reactors, right? So 2 are based on stoichiometry, 2 are based on equilibrium-based calculations, and 3 based on kinetic calculations. So among the options given, you have this one based on stoichiometry, another based on equilibrium, right? So these two which you see here based on the reactor based on stoichiometry, the ratio based on the equilibrium are the right answer for this. Okay, that was just a simple question. And then so in this figure you can see that you have a CSTR over here, right? So it's stream S1 is the inlet and stream S2 is the outlet. Okay, so the given conditions are, let's say the temperature under the label it says 250 degrees centigrade, pressure of 30 bar, and vapor fraction of 1 is the inlet condition, and the same are the outlet conditions as well. Okay, so now I want you to answer what are the valid phases in this case. So what should be filled in the option C? What are the valid phases in this system? From the given data, will you be able to answer? Or do you need any additional information to answer this question? What are the valid phases over here? So do we need any additional information for answering this question? Does anyone think that we need an additional information to answer this question? No. Okay. Anyone else? It's not required, right? You can see that the inlet vapor fraction is 1 and the outlet vapor fraction is also 1. So which means that the entire reaction is happening in gaseous phase, right? So for the valid phases, if we can select vapor, that is all sufficient. Okay. Okay, fine. So we were solving this question, right? We said we'll be simulating a separation plant. A part of it, and we just started with this heat exchanger setup in the last class. So people whoever have Aspen with you now, okay, just do things parallel to me. Okay, I'll be showing you step after step. It will be ideal if you have done it previously, as we discussed last week, and come back with the problems where you are facing, but we'll do it parallelly. Okay, so we said that we're gonna simulate the liquefaction cycle of the process in the air separation plant, right? So we said we're gonna simulate only the cold box which is enclosed in this red frame. Okay, so after finishing this exercise, we'll be understanding the calculator block as well as the optimization tool available in Aspen. Okay, okay, fine. So shall I continue with that question, or do you have any questions before we go ahead? I'll just repeat. Shall we continue where we left the last week, or do you have any questions before we proceed? Which error you are talking of, Akshay? Assignment 8 part B. Okay, I'll check it. I didn't see your assignment. Towards the end of the session, I'll check it. Okay. Which error did you get in CSTR, Akshay? Which question you're talking about? Because we didn't do any CSTR exercise in these sessions, so I don't know which question you're talking about. Okay, dependent error in CSTR. Okay, fine. Okay, I'll have to check it, okay, because I don't remember what he taught in lecture 24, synthesis of methanol. Okay, fine. I'll do one thing. I'll check it and come back the next week, okay, because I didn't see this lecture. Okay, fine. If it is coming for everyone, then probably something should be noted. Okay, I'll check it and come back. Okay. Any other questions? Assignment 8 and the CSTR issue, right? Only. Okay, fine. So we'll continue where we left. Okay. We said we're gonna simulate. We're gonna put up this setup. So let me take a fresh Aspen. Okay. So the first step in Aspen, what do? We give the components, right? We said we'll give components. We'll start with nitrogen, air. Let me add oxygen as well. Okay. So let us, for simplicity case, let us assume air is mixture of just nitrogen and oxygen, just to simplify. Okay. Then we'll go to simulation thing. So people, whoever have access to Aspen, last date for submission is tomorrow. Okay, I'll inform the concerned person regarding this. Okay, if everyone is getting an error, then there can be something done with your assignment submission. Okay, so don't worry about it. Okay. So do you have so in your assignment you have CSTR thing where you're facing an error? Is that the concern you have? If so, your assignment problem has a CSTR related question. Is that what you mean, or in the lecture 24 there is something error, right? That's what I understood from your previous point. See, you can unmute and then just talk. Probably this chat is taking me to a wrong conclusion. Oh, okay, fine. Okay, this makes sense. So you have two issues. One, there's an error in the lecture video, and the second issue is assignment. There is something missing. However, the submission date is tomorrow. Okay, fine. I got your point. If there is some data really missing, then no, it will be updated, and the assignment submission date can also be changed accordingly. Okay, I'll just take this point to the concerned person. I'll take care of it. Okay. No, I didn't see the question, so I can't tell at this point of time if data is actually missing or not. I'll have to check it. Right. So as of now, shall we continue with the thing what we are doing? With respect to assignment, don't worry about it. Okay, it will be taken care of. Something is really missing. Okay. Okay. Fine. So in this case, we said we're gonna simulate this, right? So let's just see what all the unit operations we have. We have first heat exchanger, we have second heat exchanger, and we have an expander, we have a second expander and a phase separator, right? So first let us place all these unit operations that we have over here. Okay, so we said one heat exchanger, second heat exchanger, then we said we have one splitter, right? Then expander. People whoever have Aspen with you, please do parallelly to me, okay? So that if you are getting stuck somewhere, you will know. In last semester classes, what I did was I was waiting till the students respond and they finish the assignment and then give me a response. However, during that time, all of them were having Aspen during this live session, so it was possible to do so. But now seems most of you don't have Aspen. While doing the same simulation, professor. Okay, fine. I will do this simulation first, immediately after this class. Okay, then I'll respond accordingly. Okay, just after the class I will do this, and I'll have to see what is there in lecture 24. I can't remember each and every lecture, right? So immediately after this class, I'll go back and see what is there. Okay, fine. So we'll continue here. So we said we are placing this one, right? So we have the first stream, which is hot inlet, right? Hot inlet is taken to the splitter. From the splitter, a part is taken to the second heat exchanger, right? Then the hot outlet is taken to this turbine. I think I missed something. There is something called a mixer over here, right, which I missed. So let me add mixer as well. Right. So from the turbine outlet, I have one tube. This is my liquid product. This is going to this part. I have cold inlet here. I have cold outlet. See, if I do everything, then it's hard to learn for you. Unless you do with your hand, it's really difficult to understand. So, try doing it parallelly. So, I remember few of you said you have Aspen with you, right? Can you do it? Can you start doing it and tell me your status? I'll just put this flow sheet first, then I'll wait for some time for your response, okay? Okay, let me just give the same numberings. Here's my 3, 4 certificates, 4 expander, 9 over here. So yeah, this is how the flow sheet looks once after setting it up. So can you, people whoever have Aspen, can you also do the same exercise and give me a confirmation that you are able to set up this flow sheet? So all I need to do is have 2 heat exchangers, 1 splitter, 2 expanders and a phase separator, right? So let me show you the flow sheet. So this is what we have set up. Could you follow what I did? Everyone? Any response? Yes, okay, thanks, Mr. Arun. Others? Can you reproduce the same? Will you be able to do this flow sheeting? Okay, thanks, Raj. Others? Others, can you reproduce this? Will you be able to do that? If not now, sometime later. Okay, thanks, Akshay. Can you show component? Which component, sir? The component means the initial thing. Adding components. Is that what you mean? See, what we need to do is, while searching, for example, I'll just delete this, okay? So what we need to do is click on find, okay? We'll search over here, okay? So after searching, it gives us what does it matches to, okay? Just click on it, that's all. See, the oxygen gets added to this components list, okay? So that's how we add it. Or else there's another way of doing. Let me show you. Let me delete this. You can just type it over here itself. That's a simpler way of doing it, okay? Could you follow it? Could you follow it? Is that what you asked? You asked me to show me the components, right? Okay, fine. So just click on next. What it does is, see, every mixture or components which we give, it does using binary interaction parameters, right? So we need to give a confirmation of binary interaction parameter. So this will take us automatically to this page, okay? That's what it means. So then we went to simulation module, and then we set up this flow sheet, okay? The next task for us is to give the stream data, stream information, okay? For example, stream 3. This is at ambient, let's assume for 300 Kelvin and 40 bar, 1 kilomole per second. Now we are talking of liquefaction of air, right, and separation of air into its components. So initially, to simplify the analysis, we'll assume air to be a binary mixture of nitrogen and oxygen. Okay, is 79% and 29%, just for simplicity sake. So after giving the stream input information, you can see that the stream data is complete. So that's why it turned from red color to blue color, okay? Now let's go to block. HX1. So since the aim is to optimize the operating conditions, initially we'll start with just close enough numbers, okay? Let me just cool it down to 250 Kelvin. I'm just guessing it, I don't know the actual value. This is one of our variable in optimization, okay? The temperature to which it has to be cooled before expanding in turbine, okay? So that's one of our optimization variable, okay? Even our split fraction is also optimization variable. As you see in these slides, we have three variables, T4, T5 and the split fraction. Okay, so we have three optimization variables. So initially I'll get started with some value. I'll say let me send 0.2% to the heat exchanger, and then in the second heat exchanger I'll give hot outlet, cold outlet. Hot outlet, let me give us 100 Kelvin. I'll also give the zonal profile. Okay. Then I have an expander. This is a turbine, right? So convergence, I'll say this is as liquid, because there's a chance that we have a two-phase at the outlet, and discharge pressure we are expanding it to 1 bar. Okay. And let's assume the efficiency to be 85%. Then we have another turbine towards the end. Okay, change the convergence to two-phase instead of being single phase. Discharge pressure of 1 bar. It's bar, right? Just be careful. This is about 70%. Then we have the separator. It's a heat duty is 0 and pressure drop is 0. Okay. Now after giving all this data, it says the required input is complete. Do you see this? Could everyone follow till here? Giving the input, the flow sheet may not converge at this point of time, because we are yet to optimize the process, right? The optimize the operating conditions and all. The flow sheet may not converge. We'll vary them the optimization thing. Okay. Thanks, Arun. Others, could you follow till here what I did? Okay, thanks, Raj. Others? Okay, fine. So the next step in this process is to create a calculator block. Okay, so how do we create calculator block? So the calculator block is essentially done to calculate this efficiency. Okay, so whatever we are talking about. So what I'll do, go to flow sheeting options, calculator. Here you will be able to see the calculator block, right? Just click on it. So what do I need? I need 7, 3, 12, right? So I'll say in 7, in 12, H7 is 7, H3 is 3, H12 is 12, CPW expander. What do you have then? Let's see, that's not right. So you can see the list of definitions we are about to make. So N12 is import variable, right? All the variables which the calculator need to import from some other subroutine are called as import variables. Okay. This calculator block takes all these variables from some other subroutines and exports the efficiency, whatever we defined over here, right? Thus, the efficiency becomes the export variable. Let us define each one of it. Since this is exergy efficiency, this will be output and the parameter 1. This is block variable, right? Work of the expander. Which one? XP, and what is the variable? It's the network, right? And similarly, the cryo turbine. It's also a block variable. It's CT block, net, right? Then we have stream 12. This is a stream variable, sorry, right? Select the stream variable, and then it's 12. This is entropy, right? Then we have H12, the stream variable, enthalpy. Stream. Sorry, there is a stream variable. Which stream are we talking about? Third stream. This is entropy. H3. Is enthalpy of the seventh stream, right? Select the stream and then enthalpy. So this is flow rate. Similarly, N7. So you can see that the definitions are complete, right? It says the definition is complete. Now what do we calculate? We calculate the efficiency. So before calculating the efficiency, we need to define ambient temperature as 300, right? So we have another definition of exergy, which is EX7, which is written over here, right? EXI equal to HI minus Tm. So H7 minus Tm into S7, right? Then we have 3 H3 minus Tm into S3. Then we have X12, which is H12 minus Tm into S12, right? So on the numerator side, we have N7 into EX7 minus EX3. On denominator side, we have N12 into EX3 minus EX12. Just to be careful with the sign convention, I will say ABS. Okay. What did I define for expander? WP, right? What is my EFF? So that's all. So is the calculator block okay? The property method is Peng-Robinson equation of state. Okay, it's Peng-Robinson equation of state. So the calculator block, whatever I have shown you, is this clear? How did I give the import variables and export variables, and how to give the relation between these two? We are using Peng-Robinson equation of state. Okay. Is the calculator block clear? Any response? See, okay, fine, no issues. See, all we need to do is I'll just do it. So, first of all, after coming to calculator block, you need to define the import variables. Basically, what do you want to calculate from the system? Okay. If I want to calculate the work which is obtained from both of this expander, which is net work, okay, I'll show you how do we do that. So I'll say this is W1, which is one work, second expander work, and this is W net, which is sum of these two. So W1 being an import variable, because we are importing it from the flow sheet, right? We will say W1, which is a block variable, block, and then it's the turbine's network. So if you type network, you can see, you'll be able to see the network. Okay. And similarly W2, okay, it's also a block variable, it's an import of the expander. Among all this, just look for network. Okay. And similarly, this is an output, right? This is an export parameter. Since we already gave 1 for efficiency, we'll take 2 for this. Okay. In the calculator, just go type network equal to W1 plus W2. Let us see how does it run. Okay. The simulation may not converge and give us errors because of the conditions which we get. However, you can see that a calculator block is converged, right? So if you see the network, you can see that you have some value. Okay, so it is giving some value. However, the flow sheet is not converged because of the values which we give. That can be taken care in future. Okay, so as of now we are only seeing the calculator block. So is the calculator block now? Could you follow what we did? Everyone? Yes. Okay. Thanks, Arun. Others? Okay. Great. This block is inside design spec. No. When you see here under flow sheeting options, you have multiple subtabs. Okay. So this is just below design spec, not under. So this is under flow sheeting options, but below design spec. Okay. Any other questions? Okay, fine. Let me continue. So even the efficiency, which you can see that it says 44%, right? Sorry, 0.01. When you take it in terms of percentage, it's about 44%, right? However, this flow sheet didn't converge because of the values which we gave, right? So what we'll do, we'll run an optimizer to optimize the efficiency. However, making sure that the flow sheet converges. Okay, so further, what we need to do is we need to give certain constraints. So what constraints we have? We have approach temperatures in both the heat exchangers must be greater than some certain value, and it's a single phase expander. Okay. Let us do that. So first, let us give the constraints. Says meta 1. So under this model analysis tool, you can see this constraint tab. Okay, just go to constraint, click new. You can rename according whatever you need. I'll say meta. This is my block variable. The same thing what we did in calculator block. Okay, no difference. It's just defining this. That's all. So we said that meta should be greater than 5, right? So that's what we are supposed to do. It's greater than 5 and some tolerance for that. Okay. And we need to give the second constraint. We'll say meta of 2. Second heat exchanger basically. It's a block variable. Block. Second heat exchanger. Meta. Greater than 5, 0, 1. Okay. What is the third constraint? We said the expander should be single phase, right? We said the expander should be single phase, right? We'll see which expander we are talking about. So if you see here, we said this expander should have single phase. That means inlet and outlet should be of vapor phase. So how can we give such constraint? The simple way of giving is checking the dew point of the stream 9 and the stream temperature. If I say that the temperature of stream 9 is slightly above its dew point, then it is assured that I am in vapor phase, right? Did you get this point? If I am at a temperature above its dew point, I am sure that I am in vapor phase, right? So giving this constraint will help me an indirect way of setting that this expander is in single phase. So that will be my third constraint. This is T2. Okay. So I'll say T9 and T9 do. Go to stream 9. Temperature. Similarly, the dew point temperature we need to give calculate it, right? So it will be stream property. Okay. Okay, stream 9, we want to calculate dew point. Okay, so we said stream 9 value should be greater than its dew point. So it's stream 9 dew. It should be greater than, let's say, 2 Kelvin. Tolerance of 1. So this ensures that my stream 9 is always in vapor phase because my stream temperature is greater than its dew point, right? So this is indirect way of giving the constraint. Now once the constraints are set up, all we need to do is call the optimizer. So click on optimizer, new. We need to define the efficiency term which we have previously defined in calculator. So we gave the number 1, right? So make sure that you also give the number 1 over here. Okay? Once we give number 1, so we need to maximize EFF. These are my constraints which need to be satisfied. Then you can see a vary tab over here. So once you go to vary, so what are the variables we have? We have 3 variables, right? It says T4, T5 and the stream fraction. Okay. So in this figure, if you see, T4 is hot outlet of the first heat exchanger. Similarly, T5 is the hot outlet of the second heat exchanger, right? So both of these can be defined as block variables instead of defining as stream variables, right? So all we have is 3 variables in this setup. So my first variable is block variable for Hx1, right? It's hot outlet. If you see, you can see the specified hot temperature 83. My lower limit is 200 Kelvin. Let's take an example, and upper limit is 280 Kelvin. Okay? And similarly, the second is another block variable, another hot outlet, right? This is second outlet, and then I have temperature. So this one can be the lower limit of 90 Kelvin to about 140 Kelvin, let's say. And third one is the block variable of this split, right? So here is the split. So let me just confirm what is the input which I gave with the split. So I said 4P. Right? So you need to give the same value over here of the ID 4P. So 4B, let me choose from 0.1 to 0.9. Okay. So till now everyone could follow what I did. Could you follow? Yes. Okay. Thanks, Arun. Others? Akshay, Ankit, Maru. No. Okay. Which point did you didn't catch, Akshay? Okay. Just do it, and in case if I'm getting stuck, just get me. Okay. So that's all we need to do with the optimization. Okay, just try running this. So let's see what happens. See, now we have some results, and it says results are available, right? Once the optimizer is run, you can see that all constraints are satisfied, they are inactive. And in the manipulated variables, you can see that although initially we gave some value, the final value is something different, right? So if we want to get the output results of the optimizer into our input stream, all you need to do is just reconcile your results over here. You can see on the top something called reconciliation. Just reconcile, click OK, and OK, that's all. So this will take all the output that we obtained from optimizer to our input variables. Now you can deactivate the optimization block and just run the flow sheet. See, now you can see that the simulation has converged. You get error because there's a two-phase expander over here. Okay, so because of this, it says let us check the. Let me show you. See, you can see that this cryo turbine has the warning. So what it says is it has got two-phase entry. So that's what it means. Okay. So could you follow the calculator block and the optimization? So once you do it, you will come to know where are you facing the difficulty. Okay, so unless you do, it's just too difficult to just follow this class. Any question would you like to ask in this? The optimization and the calculator block? Okay, if not any questions, let me just summarize what I did. So the basic idea is to simulate the entire plant. Okay, so as of now we have simulated this part of the process. So in the coming class we'll simulate this part. Okay, but so what we did is the heat exchanger setup, which is the liquefaction cycle. Okay, which is called as Kapitsa cycle. Okay. So we said that this particular liquefaction process has got about 5 unit operations, sorry 6. We have a mixture here as well. So we initially set up the flow sheet with 6 unit operations, and then we connected the streams with we randomly gave the input information because we don't know what all the operating conditions that maximizes the efficiency, which we defined in terms of the exergy losses in the system. Then once after defining the giving the input data required to simulate the process, we found that the simulation was failing to converge. Then we went to calculator block. We created an efficiency. We said we defined our input variables and one the efficiency as the output variable. So in the calculator under the Fortran tab, we gave the data and the calculation formulations whatever we have in our system. Right. Then what we did is we went to optimization tool and just clicked on constraints. So we added three constraints to this problem. So we said the internal temperature pinch in heat exchangers 1 and 2 should be greater than certain value. Obviously, right, we can't have crossover between hot and cold streams. So what is this internal temperature pinch? Is the minimum temperature difference between hot and cold streams, right? So if we have crossover between hot and cold streams, it's the crossover and it violates the second law of thermodynamics. So we said we'll have minimum internal temperature approach of greater than certain value. In this case, we took 5 Kelvin. And the third constraint which we said is the expander, which we are using is a single phase expander. So how did we manage to make it as a single phase? We said the temperature of stream 9 should be greater than its dew point temperature. This makes sure that the stream condition is in vapor phase, right? So that's the only thing which we did, the three constraints. So once after defining the constraints, we went to the optimization block. We defined the objective function, which we have initially written in the calculator block. We gave the same parameter number so that there is a pointer which links between these two. Then we said we defined we are trying to maximize the exergy efficiency which we defined, and these are the three active constraints which we have selected. Then what are the variables we have in our system? We said we have three variables, right? T4, T5 and the split fraction. So T4, instead of directly defining it as a stream variable, we can define it as a block variable outlet temperature. So the T4 becomes a hot outlet of the heat exchanger 1, and similarly T5 becomes hot outlet of the heat exchanger 2. So that's how we define our variables. So we said let me just extend this. We said my first variable is hot outlet, stream 3, and similarly my second variable is hot outlet of heat exchanger 2, right? And third one we have the split fraction in the splitter. Whatever we have this split fraction. To what fraction should we send it to the expander or to the heat exchanger? So that becomes our third variable. So once keeping everything ready, once we run the optimizer, we have a converged value, and it says that the efficiency which is calculated at the converged value is about 48%, right? Which is about 48%. So that's how we have simulated this process and optimized it. So yeah, I hope you got it. And once you just try it out, unless you try it out, you can't just say that you understood it, or you do one thing, you just try it out. In case if you're getting stuck somewhere, you can come back next week and we'll continue. Okay, but we'll start with the distillation setup the next week. However, if you are stuck with respect to this question somewhere, look, we'll come back to this as well. And I'll check your assignment problems which you have pointed out, and I'll see if it is a genuine case. Then for sure I'll report the same to the concerned person. Okay. So do you have anything else that we should discuss at this moment? No. Okay. That's great. So in that case, we'll come back next week. Okay. Thank you. Thank you very much for your response. So in that case, I'll just stop this lecture and we'll come back next week. And thank you very much for class. I'll just stop the recording.